Hi everyone, thanks for tuning in. This is a project to improve the estimation of sea surface height between sea ice leads along altimeter tracks in the Arctic Ocean. This has been done with co-authors from ESA, NOC and UCL. And I just want to acknowledge funding from the ESA Living Planet programme, which has been supporting my research at the University of Bristol. So the background for this project: conventionally we use elevation estimates at leads as tie points for interpolating SLA along altimeter tracks where we have no observations, and we get uncertainty estimate from the variability of lead elevations and the distance of an ice floe from its closest lead. But we usually have to discard a selection of the data where lead densities are too sparse. So the objective here is to see if we can use leads from other altimeter tracks too to improve the estimation of SLA and its uncertainty. So here we've used an objective mapping scheme that is similar to Gaussian process regression. At every sea ice floe, we gather leads from all local tracks. We impose random and systematic errors for each lead observation. And then we assume a modified Gaussian function characterizes the space-time properties of the SSH signal. So we need to understand the space-time scales of this signal and how it propagates before we can account for the expected dynamics of mesoscale ocean variability and get a better estimate for local SSH from all valid leads. So first we determine the Panarctic characteristic, spatial and temporal E-folding length scales of the SSH signal. And here we've used the full archive of Cryosat-2 winter lead observations to do this. And it suggests that we can use leads several hundred kilometers from and a few days prior to and after each Cryosat-2 orbit to determine the local SSH more accurately. But these length scales are about 1 order of magnitude larger than the baroclinic Rossby radius of vertical ocean deformation. So we've also tested the identical method, but using SSH fields from a NEMO model simulation with a resolution of a few kilometers in the central Arctic, which should at least be eddy permitting. And the SSH is available for every grid cell, not just at leads, as we have with the altimetry data. But we obtain similar length scales from the NEMO fields to the Cryosat ones, and it also demonstrates larger scales in the ice-covered region than the ice-free ones. Our covariance analysis of Cryosat-2 data also determines the nugget and SIL variances of the SSH signal, but I won't talk about them in detail here. So how well does it work? Well, this is the same track as the opening slide. Each point here is a lead from this or another track, with the color scales showing the covariance to the ice floe at that location. The black line is the final determined SLA, and the dashed line its uncertainty. So we can see, for example, the SLA tied to leads on track and higher uncertainty in lead sparse areas. What's clear from a comparison of the conventional and the new methods is the new method resolves much finer detail of the SSH, if it's true, of course. And it also highlights that the derived sea level is not tied to single isolated leads along track, as the conventional method can be. This indicates here, for example, with the lead on the left, that it probably has high error. It's identified as an anomaly by analyzing the covariance matrix of its lead neighbors. If we run the new method for an entire month, we don't find any mean bias in derived radar freeboard compared to the conventional technique, but there are small long wavelength differences in the methods along track, so it produces a mean unsigned uncertainty of 27%. The obtained uncertainty is also based on the covariance matrix of lead observations, so it's much more data-oriented than the conventional uncertainty estimates. And because the SSH estimate is obtained from 10 to 100 times more leads, it's about a factor of 3 lower than the conventional error estimates. To evaluate how well the method is working, we first looked at orbital crossovers, and we found that the estimated SLA at crossovers is reduced by about 70%. And the derived radar freeboard is reduced by about 19%, indicating that potential biases in the determination of SSH account for about a fifth of the RMS of freeboard at crossovers, and the rest will be ice related. We also compared to radar freeboard estimates from airborne OIB campaigns, where the conventional and the new SLA methods diverged. We wanted to see which was closer to the airborne data. So we found in 2 flights, this is just one of them, that the objective method could remove biases evident in the radar freeboard distributions determined from conventional interpolation. And this is just a summary of the key points I've made here in the presentation, but please let me know if you have any questions and I'll be happy to chat. Thank you.